Hello students, I am Professor Urvish Mewada, HOD Electrical Department, Sri Swaminarayan Institute of Technology, Gandhinagar. I am the subject matter of Interconnected Power System subject, which is in the 7th semester Electrical Engineering, and GTU subject code of this subject is 2170901. Students, currently we are discussing the chapter number 4, Economic Operation of the Power System, in which this is our lecture number 4, and we are going to discuss our last topic 10, that was the example which was based on the chapter. So in this we are continuing with this topic number 11, examples which are based on the chapter or other methods which are means the methods which we have discussed in the theory section, and the examples which are based on that the different theory section of the chapter. Now, before we start with the today's lecture, we will just recall the previous lecture. In lecture number, in previous lecture, lecture number 3, we have discussed the topic number 9, in which we have discussed the unit commitment and power system in detail. And in unit commitment, we have discussed the method that we applied, the advanced method for the computing technology, means the computational technology for the unit commitment that we applied for the unit commitment in the power system is unit commitment using dynamic programming method. So we derived the equation of that dynamic programming method in detail, and then we have discussed the advantages related to the unit commitment of the particular generating station, and then we have discussed the examples which are based on the current chapter in topic number 10, and this is the continued topic of topic number 10, and this is topic number 11 for this particular lecture is example based on the chapter of economic operation of the power system. Now let us discuss the examples. So such kind of examples are frequently asked in the GTU exam, so please go through it carefully, and please try to solve it by your way. Example number 1, a two bus system is shown in figure. This is the diagram in which the two bus system is shown. If 100 megawatt is transmitted from plant number 1 to the load, a transmission loss of 10 megawatt is incurred, and find the required generation for each plant, and the power received by the load when the system lambda is 25 megawatt hour. So this is the data which is given, and dci by dpgi is equal to 0.02 pgi plus 16.00 rupees per megawatt hour, and dc2 by, this is the incremental cost of c1 and c2, and dc2 by dpg2 is equal to 0.04 pg2 plus 20.00 rupees megawatt hour. So this is the data given. Now let us find out the solution from the data given. In this we have the two generating station, plant 1 and plant 2. The plant 1 is connected with the bus bar, and after bus bar number 1 we have the transmission line, and then after we have the bus bar number 2. With bus bar number 2 we have the plant number 2 is connected, and with the bus bar number 2 we have the load which is connected, at which we are delivering the power PD2. Now from the diagram we can say that load is connected at bus number 2, so we can write b22 is equal to 0, and b12 is equal to 0 is equal to b21, because 2 is connected over here, so there is no transmission losses, so that's why we consider only the bus number 1. So yes, we can write pl is equal to b11 p1 square, so that pd1 is equal to 0 because power delivered at 1 is equal to 0, and pg1 is equal to p1, and pg1 is equal to, that is given over here, 100 megawatt, and pl, that is given transmission lost incurred, that is 100 megawatt, and therefore we can write the equation, the pl is equal to b11 p1 square, so pl is the 10, so 10 is equal to b11 100 square, so b11 is equal to 0.01 megawatt inverse. So this is the value of b11 from the given data. Now for the plant number 2 we have the equation, that is 0.04 pg2 plus 20.00. so for that the equation is lambda 1 minus del pl by del p del P2. So in this we have put the value of del PL by del P2, it is 0 for this condition, so is equal to lambda. This is the equation for this, we can write is equal to lambda. Now substitute the value of B11, 0.01 megawatt inverse, and lambda is equal to 25. We get Pg1 is equal to Pg1 is equal to, that is 128.557 megawatt, and Pg2 is equal to 125 megawatt. Now transmission power loss we can determine from this given value. PL is equal to B11 P1 square is equal to 0.01 into P1 that we have determined from this, that is Pg1 128.57 square. So PL is equal to 16.53 megawatt, and the load is PD2, so Pg1 plus Pg2 minus PL is equal to PD2. So Pg1 is 128.57, Pg2 is 125, so plus 125, and the loss that we have determined PL is equal to 16.53. so this is the system which requires 237.04 megawatt, it means it will be it will deliver this PD2, means requires this much amount of power to deliver towards the load which is connected with the bus number 2. Now let us discuss the example number 2. So in this diagram, figure shows that having two plants. So over here you can see that generator 1 and generator 2 both are connected in the system. So two plants 1 and 2 connected to the bus number 1 and 2. So this is the bus number 1 and this is bus number 2 respectively. So there are two loads which are connected over here. One is connected with this line and one is connected with this line. The reference bus with a voltage of 1.0 at angle 0. So reference bus which is connected over here, you can see that this is the reference bus at which the voltage is 1 at angle 0. PU is shown on the diagram, so which is indicated over here, and the branch current and the impedances which are given for particular branches. So IA, IB, IC and ID, we have the four branches. So you can see that this is the IA, this is the IC, this is the IB, and this is the ID. All the branches having the value of the current and the impedance, so which are shown over here. Now calculate the loss formula coefficient of the system in PU and in the say reciprocal megawatt if the base is 100 MVA. So we need to calculate over here the loss formula coefficient of the system in PU and say in reciprocal megawatt, so megawatt inverse if the base is 100 MVA selected. So this is the data given. Now let us find out the solution for this. So in this from the given figure we can calculate the IC upon IC plus ID. This is the equation that we have already discussed in the theory section. So IC is given 1 minus J 0.25 and IC plus ID is 4.6 minus J 1.15. So from that, this is the ratio, that is 0.2174 that we get from IC upon IC plus ID. And what about the ID upon IC plus ID? So that is 3.6 minus J 0.9, all the values which are given over here. You can see that 3.6 minus J 0.9 and IC plus ID is 4.6 minus J 1.15. So for that, this is the value that we get from ID upon IC plus ID. Now we have the equation of say power system, in which we have we determine that MA1, MB1, MC1, MD1 for the respective impedances. So for MA1, MA1 is 1, MB1 is minus 0.2174. Over here you can see that minus 0.2174 and MC1 is 0.2174. This is the value that we get, and MD1 is 0.7826. This is the, from that we can write MA2 is equal to 0, then MB2 is equal to, this is 0.7826, and for MC2 it is 0.2174 and MD2 is 0.7826. so we can write all the values from this equation, and let V1 V2 are the plant's bus voltage. So V1 is equal to, we can write equation over here, 1.0 plus, this is the value which is given over here, 1.0 plus 2.j 0.5 into 0.015 plus j 0.06. So after solving this, we can find out v1 is equal to 1.06 plus j 0.1125. So this is the a plus j b form. Now r angle theta form of this v1 is 1.066 at angle 6.05. Now for v2, we can write the equation, that is 1 plus 1 plus 1.6 minus j 0.4. These are the value that is given over in the data, and 0.015 plus j 0.06. So after solving this, we will get this output, means voltage v2 in terms of a plus jb form, that is 1.048 plus j 0.09, and r angle theta form of this v2 is 1.051 at angle 4.9 degree. Now the current phase angle at the plants are, say, I1 is equal to IA, I2 is equal to IB plus IC. So this is, you can write from this over here. So this are the value, means meeting of the branches. So you can write down the equation from this. So theta 1 is equal to tan inverse of minus 0.5 by 2, so it is minus 14, and theta 2 is equal to tan inverse of 0.665 divided by 2.6, so it is minus 14 degrees. So cos theta 2 minus theta 1 is equal to cos 0 is equal to 1. So the power factor of the plants are, say, cos theta 1 is equal to power factor 1, that is cos 6.05 degree plus 14, that is 0.9393, and cos theta 2 is equal to pf2 cos 4.9 plus 14. We have added the value of theta that we have determined in the previous slide, that is 0.946. Now the loss coefficients are from the equation 4.29 and 4.30. So that is b11. This is the equation for b11 by after putting all the values in b11. So that is 0.02224 pu, and b22, so that is 0.01597 after putting all the values in the b22, and b12 is, this is the equation that we have already derived in the theory section. So this is the 0.0406 pu. Now 100 MVA base is given, so that b11 is equal to 0.2224 224 divided by 100, so it is 0.02224 into 10 raised to minus 2 megawatt inverse. Then b22 is 0.01597 divided by 100, so it is 0.01597 into 10 raised to minus 2 megawatt inverse, and b12 is again 0.00406 divided by 100, so it is 0.00406 into 10 raised to minus 2 megawatt inverse. So this is how we can solve the parameters related to the given from the given data. So here we have calculated the loss formula coefficient of the system in pu, and then we have calculated the reciprocal megawatt if the base MVA is 100 MVA. Now let us discuss the another example. So example number 3, in this it is given that the system is consisting of two plants which are connected by a transmission line as shown in the figure. The load is at plant number 2. The load is at connected at plant number 2. If a load is 125 megawatt is transmitted from the plant 1 to the load, then there is loss of 12.5 megawatt. Determine the generation schedule and the load demand if the cost of the received power is 70 rupees per megawatt hour. Assume that the incremental cost of the two plants are given as, these are the incremental cost that is given for the particular plants. So dc1 by dp1 is equal to 0.025 plus 0.25 into p1 plus 40 rupees per megawatt hour, and dc2 by dp2 is equal to 0.20 p2 plus 50 rupees megawatt hour, rupees per megawatt hour. So solve the problem using a coordination equation, and second one is penalty factor method. So we have already discussed these two methods, so let us apply these two methods over here in the example. So since the load is connected at the bus number 2, so b12 b21 is equal to 0 and b22 is equal to 0. So only we have considered the branch number, means bus number 1. So for a plant number 2, the PL is equal to P1 square B11 P2 square B22 2 P1 P2 B12. So yes, where P1 is equal to 125, it is given. PL is equal to 12.5 megawatt, it is also given. So we have 12.5 is equal to 125 square into B11 plus 0. So that's why B11 is equal to 8 into 10 raised to minus 4 megawatt inverse. So therefore we can write PL is equal to 8 into 10 raised to minus 4 P P1 square. So where del PL by del P1 is equal to 60 into 10 raised to minus 4. We can determine using del PL by del PI. So first is using coordination equation. So for the coordination equation for plant number 1 is given as dC1 by dP1 plus lambda del PL by del PI is equal to lambda. So substitute the values of this dC1 by dP1, lambda, and dPL del PL by del P1. So we will get this values, after putting the values we will get this solution, that is 0.25 P1 plus 40 plus 70 into 16 into 10 raised to minus 4 P1 is equal to 70. So yes, after solving this we will get P1 is equal to 82.8729 megawatt. And the coordination equation for plant 2 is given as this is the equation for plant 2, only the difference is 2 is applied over here. So after putting the values, the answer is P2 is equal to 100 megawatt. So the line loss is given by PL is equal to 8 into 10 raised to minus 4. This is the PL. So P1 square is equal to 8 into 10 raised to minus 4 into 82.8729. So this by applying this we will get the value of P1, that is means the line loss and at the P1, that is 5.494 megawatt. So the total load, the which is power delivered at PD is equal to P1 plus P2 minus PL. So P1 it is that we have calculated in the from the previous slide, that is 82.8729, and P2 is 100, so that's why it is plus 100 minus 5.9494. So the PD we'll get after the solution is 177.3789 megawatt. Now case number 2, using the penalty factor. So this is the equation for the penalty factor, in which we have the value of del PL by del PI. It is 60 into 10 raised to minus 4 into P1. So after applying this for optimal dispatch, L1 dC1 by dP1 is equal to lambda. So therefore 1 upon 1 minus 16 into 10 raised to minus 4 P1 into 0.25 P1 plus 40 is equal to 70. This is the equation that we can form for optimal dispatch for the given plant, or 0.25 P1 plus 40 is equal to 70 minus 70 into 16 into 10 raised to minus 4 P1. So P1 is equal to 30 by 0.25 plus 0.112. This is the solution that we get from the above. So 82.8729 megawatt is the P1. Now the penalty factor for plant number 2. So L2 is equal to 1 upon 1 minus del PL by del P2. So 1 upon 1 minus 0 is equal to 1. So for optimal dispatch, L2 into DC2 by dP2 is equal to lambda. So yes, by putting all the values we can get the value of P2 is equal to, that is 20 by 0.20, so it is 100 megawatt. And over here you can see the 1 into 0.20 P2 plus 50 is equal to 70. So after solving this we will get the P2 is equal to 20 by 0.20, so that is why it is 100 megawatt. Now let us discuss the example number 4. So that will be more clear to you. So yes, such kind of examples are repeatedly asked in your GTU exam, so please go through it carefully. So in this example number 4, a constant load of 300 megawatt is supplied by two 200 megawatt generators. So 300 megawatt is supplied by two 200 megawatt generators 1 and 2, for which the respective say incremental fuel cost are these are the fuel cost that is given. dC1 by dPg1 is equal to 0.1 Pg1 plus 20, and dC2 by dPg2 is equal to 0.12 Pg2 plus 155. So with power Pg in megawatt and cost C in rupees per hour, determine A, the most economical division of the load between the generators are, and means this is the first task that we need to perform, that is the most economical division of the load between the generators. So we need to find out that how much amount of load will share by each of the generators, and the saving in rupees per day thereby obtained compared to equal sharing between the machines. So yes, after sharing the load by the generator, we need to calculate the saving in the rupees per day which is obtained compared to equal sharing between the machines. machine. Now solution, let us find out the case A. That is, first is incremental fuel cost of the first generator. It is given IC1 is equal to DC1 by dPg1 is equal to 0.1 Pg1 plus 20. So the incremental fuel cost of the second generator is IC2 into DC2 by dPg2 is equal to 0.12 Pg2 plus 15. It is given. Now for optimal load division, the two incremental cost should be equal. So IC1 is equal to IC2. So let us compare this two equations. So 0.10 Pg1 plus 20 is equal to 0.12 Pg2 15 plus 15. So yes, 0.10 Pg1 plus 0.12 Pg2 is equal to minus 5. This is equation number 3. Now the total load is shared by the two generators. So Pg1 plus Pg2 is equal to 300, because total load which is transferring by two generators is 300. So saving equation, that is means by say saving equation number 3 and 4. So Pg1 is equal to say 140.9. so by after solving this and putting the values in this, we will get Pg1 is equal to 140.9 megawatt, and Pg2 is equal to say 159.1 megawatt. Now in the case of B, the cost of the generation for each units are, say, C1 is equal to integration of dC1 by dPg1 into dPg1. So yes, we can put the values of dC1 by dPg1, that is 0.1 Pg1 plus 20 into dPg1, and after integrating this value, we will get 0.05 into Pg1 square plus 20 Pg1 plus K1 rupees per hour. So this is equation number 5. And for the C2, that is integration of dC2 by dPg2 into dPg2. So integration of 0.12 Pg2 plus 15 into dPg2. So the values after integrating the above equation will get 0.06 Pg2 square plus 15 Pg2 plus K2 rupees per hour. So yes, where K1 and K2 are the constants. So incremental fuel cost for unit number 1, so that is C1 is equal to C1 into 150 minus C1 into 140, that we have already derived for this. So after putting the values, we will get that 314.359 rupees per hour for C1, and for C2, that is C2 into 150 minus C2 into 159.1. So yes, after putting this, we will get 305 minus 305.268. So yes, the net saving C1 plus C2 is equal to 314.359 minus 305.268, so 9.091 rupees per hour. So net saving per day is 0.9.091 multiplied by 24, so it is 218.18 rupees per day. So this is how we can solve the example related to the fuel cost and then the net saving of the generating units. Now let us discuss the example number 5. A system having two generating units connected through a line has the following loss coefficients. So loss coefficients which are given over here: B11, that is 0.1 into 10 raised to minus 2 megawatt inverse, B12 is equal to minus 0.01 into 10 raised to minus 2 megawatt inverse, and B22 is equal to 0.13 into 10 raised to minus 2 megawatt inverse. So power is being dispatched economically with P1 is equal to say 120 megawatt and P2 is equal to 200 megawatt. So both are transferring power 120 and 200 megawatt. To raise the system load by 1 megawatt, if you want to increase the load by 1 megawatt, cost an additional ₹40 per hour. So find the penalty factor of the plant 1 and the additional cost per hour to increase the output of the plant 1 by 1 megawatt. So this is the data which is given for the calculation. Now let us find out the solution. First of all, the case number 1, for a system with the two generating units, we are having generator means loss equation, that is PL is equal to P1 square B11 plus P2 P1 2P1 P2 B12 plus P2 square B22. So yes, for del PL by del P1 for of this equation is 2P1 B11 plus 2P2 B12 plus 0. So yes, after putting the values of all the parameters that is given in the data, so 2 into 120 into 0.1 into 10 raised to minus 2 plus 2 into 200 into 0.01 into 10 raised to minus 2. So del PL by del P1 is equal to is equal to 0.2. So penalty factor for the unit 1 L1 is equal to 1 upon 1 minus del PL by del P1. So it is 0.2 that we have determined in the previous slide. So 1 upon 1 minus 0.2, it is 1.25. And for case number 2, so lambda is equal to 40 rupees per hour. So we have the L1 del C1 DC1 by dP1 is equal to lambda. So L1 that we have already calculated, 1.25 into DC1 by dP1 is equal to 40. So DC1 by dP1 is equal to 30 rupees per megawatt hour. So this is the value of incremental cost of the system for the generating unit. So after this presentation, you have the exam means assignment questions. You have two examples that you should calculate. This such kind of examples are repeatedly asked in your GTU exam. So please do proper preparation of such examples. So you can take the snap of this example also, means this slide also, and if you have any query or doubt related to these topics, then feel free to ask me anytime, and we can solve your doubt in our doubt solving session. Also, if you have any doubt or query after this presentation or after this chapter completed, then feel free to call me anytime to solve your doubt related to this chapter. And the related instructions which are written in this slide, please read it carefully and follow all the instructions as given. And thank you very much, student. Thank you very much all for this presentation. Jai Swaminarayan. Thank you very much.